All right, let's start. Do you have any questions? Okay, so let's revisit what we did last time and let's, codify a little bit. I have some slight modification I want to talk about. So we did 3.3, right? Basically, I don't know, something like face portrait, right? Or, sketching, right? Solution curves in the case of, 2 by 2, right? Distinct real eigenvalues. Okay. So along this sketching, right, there is a solved question of classifying, right, the nature of the equilibrium. So in all this case, right, 0, 0 is the only equilibrium solution. The reason, right, is because we assume the eigenvalues are non-zero. So the matrix, right, the matrix y prime equals to ay, right? The matrix A is invertible in this under this assumption. So y equal to 0, right, is the only solution. A, right, y equal to 0. All right, that's why 0 is the only equilibrium solution. So we have 3 cases, right? So first case is when both eigenvalues are positive. Then in this case, the origin, right, is a source. All right. And here is where I want to kind of scratch what I said last time. So in other words, right, I did say something about asymptotic. Okay. I didn't say, I did correct myself last time, but scratch that, okay? The right way to look at this should be something like sketching solution. All right. Okay, so how do we go about this? So again, first and foremost, we always have 2 eigenvectors, okay? We always have 2 eigenvectors, which gives us 2 straight line solutions. Okay, this is true, right, across the cases. And for purpose of demonstration, okay, like let's say, suppose, right, they are 1, 1, okay, and minus 1, 1. All right. So when you want to sketch the solution curve, right, first of all, you draw the 2 straight line solutions. So let's call this y1, y2, or xy, right? And you have the 1, 1, and you have the minus 1, 1, right? Okay. And then you draw the arrow from these, right? And they're both positive, so they go away. All right. So depends on the question, but let's say you want a solution curve, I don't know, let's say starting at, let's say 0, 1. Okay. What does that mean? What that means is we want a solution curve, right? That, or maybe let's not say starting at, but let's say crossing. Okay. Crossing 0, 1. Okay. So in other words, we want a solution curve, right, that goes through this point. Okay. So then the question is, right, how do we, I mean, ignore that, right? That's not really a curve, but the solution curve must cross through this point. How do we sketch such a curve? Remember, right, that the point is that the solution, right, the solution curve will diverge. It will go away to infinity. But how would we do it, right? How we do the question is actually, of course, we assume, let's say lambda 1 is bigger than lambda 2, let's say, right? For concreteness, let's say lambda 1 is 2, lambda 2 is 1, right? So the trick is, right, what I said last time was wrong in the sense that as t goes to infinity, right, as t goes to infinity, I say because lambda 1 is bigger than lambda 2, it should be close to v1. That's not true, right? Actually, the opposite is true. That is, we don't look at this so much, but as t, right, approach minus infinity, okay? As t approach minus infinity, then the solution does approach v2, okay? The solution approach v2. Yt, okay, approach v2, because it's the dominating term. Yt, right, approaches the straight line solution associated with v2, okay? Now again, this has to do with this assumption. So let me write down for you, right, that Yt is C1, right? 1, 1, e to 2t plus C2, 1 minus 1, right? E to t under this example. But now if you push t to minus infinity, right? If you push t to minus infinity, first of all, right, both of them go to 0. So it starts at 0, okay? They start at 0. But on the other hand, right, they start at 0, but then because this term, right, is dominating, this is less 0 than that one. In other words, this term is much smaller than this one because of the e to 2t. Then in that sense, right, the solution will be close to the v2 direction, okay? When you are from minus infinity, right? And then it will go out. So it start from here and then go out. So how do I want to say this, right? It'll go out. So I want to say it goes out like this, right? That's one solution. Now I wonder how you would draw a solution that goes through this point. Sorry, give me a moment. So basically, first of all, I want to say that solution will look like this, okay? In other words, it will be close to V2 from minus infinity, right? And then it will go out like that. It will go out like that. Then maybe I shouldn't even bring out this point. It's a little bit hard to navigate through this. Maybe I'll just say sketch a few solutions curve. Okay. So the point I want to make is, right, as t goes to minus infinity, the solution is close to V2. So when you reverse time, right, when time goes from minus infinity forward, it will start out from V2, right? It will start out from V2 and go outward. It will start out from V2 and go outward, right? Like this. Is that okay? So that's why I want to kind of correct about what I said last time for the case lambda 1, lambda 2 positive. You sketch the solution by tracing, right? By tracing what straight line solution it is close to when t goes to minus infinity. And starting from there, it goes out. It goes out and diverges out. Any question on this part? Okay, so we'll take a look at the picture in the textbook, right, that corresponds to this case. The second case is when they have opposite sign. Okay. Yeah, so we have three cases. All right. Case one is when both of them are positive. Case two is when they have opposite sign. And case three is when both of them are negative. All right. I think the other two cases are clear. The case one was when I described it wrong. So I want to correct myself on that. Okay. So again, right, starting from the eigenvalue, right, the straight line solution associated with the lower eigenvalue, and then it comes out. When they have opposite eigenvalues, okay, then the point, right, is a saddle point. Okay. So again, let's suppose that let's say lambda 1 is -1, lambda 1, lambda 2 is 1. Okay. Then let's say you sketch a few solutions curve. All right. Again, we will draw the straight line solutions. Okay. And because lambda 1 is -1, right, it goes in on the V1. Lambda 2 is 1, so it goes out on the V2. The solution curve here, I think, is clear, right? It kind of follows the arrow, like that. So here it's quite intuitive. We don't even need to argue things out that much. Should be like that. Is that okay? The last case, right, is when both of them are negative. All right. So then in this case, 0, 0, right, is a sink. And then let's suppose, right, let's say lambda 1 is -2, lambda 2 is -1. I think let's change it. Let's do -1, -2. Okay. And again, let's sketch a few solution curves. Right. So what do we do? Two straight line solutions. Right, but they both go in. All right. Now, here the asymptotic makes sense. The asymptotic is as t goes to infinity, okay? The asymptotic here is as t goes to infinity, yt, right, will be close to the straight line solution corresponding to the eigenvalue with smaller absolute value. Okay. So in other words, it'll be close to the V1, right, in this example, because lambda 1 is -1. In other words, right, it'll come in like this. It come into 0, right? It'll come into 0 because 0 is going to be a sink. All right. So it's like the first picture, right? But the first case, you mean here? Thank you. I draw the wrong arrow. Thank you. Someone mentioned that the arrow was wrong. Sorry. The arrow is like this. Sorry. Yep. Thank you. Yeah. All right. So yeah, the arrow is supposed to come in on both sides. So thank you. And right, but the point is, right, it will come in. So 1 and 3, you see, are like the same picture, with just the clock reversed, right? There's an asymptotic for 1, but the asymptotic is as t goes to minus infinity. So it's like the origin of the universe, if you will, right? Once upon a time, you start somewhere there, and then you go out. Of course, right, here in the picture, you cannot make it very clear, but technically speaking, right, you will never have anything starting from 0, because that's when t equals to minus infinity. There's no such thing, right? But of course, in the picture, you can flush the detail a little bit for this case, right? Same thing here, right? That you probably will never have any solution that exactly touches 0, because that requires t goes to infinity. But, right, I mean, like, you can draw that roughly on the graph. So any question here in the 3 cases? Okay. So again, right, the goal is to classify the equilibrium and then to sketch a few solution curves. Very much like the one-dimensional case, right? We do that too. But here, right, we have more complexities. Okay, so let's show you the picture from the text again, right, to kind of highlight that this is exactly what happened in the textbook, right? So here, right, the picture I want to show exactly is this picture, all right, where they have, right, 2 eigenvalues being positive, all right, and right here they say solution move away from the origin. So what they mean, right, is that the origin is where you start, but that starting point is like t equals to minus infinity, all right? So, but then there is that taste, so move away from the origin, right? But which direction does it move away from? Well, so look, right, lambda 1 equals to 4, lambda 2 equals to 1. So it should move away from V2, right? Move away from V2. And clear enough, right? Minus 2, 1, it moves away from V2. All right, so the direction should be like that. Any question? All right, so that should correct and straighten out, right, what I want to communicate on the sketching of solution curves in that case. Now then, moving on to 3.4, right, with the case where we have complex eigenvalues, right, with analytical solution. And well, let's repeat ourselves, right? But let's maybe do a different example. So let's say, no, I'm not continuing. I'm still kind of repeating what I said. Then we'll continue. Yeah, still kind of like rehearsing the old materials a little bit. So let's take a look at the text problem 4, okay? Section 3.4, where they look at y prime equals to 2, 2 minus 4, 6y. All right. So again, right, the drill is the same thing. Start with the a minus lambda I determinant, which is 2 minus lambda, 6 minus lambda, plus 8, right? So what is that? That's lambda square minus 8 lambda, right? And then plus 12 plus 20. So that's lambda minus 4 squared, right? Minus 4 squared gives you 16. So that's plus 4 equal to 0. So lambda is 2 plus minus 2i. Are we okay on this? All right, so now what we do next, right, is we search for eigenvectors, except that in this business, all right, we only need to work on one. So who knows, right? Let's say lambda equals to 2 plus 2i, let's see. Then what's v, right? So first of all, plug in, you got minus 2i, 2, minus 4, 4 minus 2i, right? So the key, right, is yeah, but wouldn't that be 4 minus 2i? The right, Will? I mean, I don't see why you need to correct me on that. The key, right, is to here, because you know that, right, these two equations will be the same because the matrix should have rank 1, right? So we just need to look at one of the equation, and I guess the solution, right, easily is let's say I, right, pick I to make it easy, and then that will make it a 2, so I have minus 1. All right. Now do yourself a favor too, right? Hold on. And check that this also works on the bottom, but I think something doesn't look right because it shouldn't work on the bottom, right? Because if you plug in, you got minus 4i plus minus 4 minus 2i. That's not equal to 0. Something is wrong. Did I solve for it wrong here? Lambda square minus 8 lambda plus 20. Oh, eigenvalue. I see. I see. I thought you correct me on this entry. Thank you, Will. Okay. Yes. Yes. Thank you. Yeah, that's why this doesn't come out. You see, I know exactly this doesn't come out, so I know something was wrong. Thank you, Will. I thought you were correcting me on this. Yeah, eigenvalue was wrong. Yep. Okay. So yeah, I mean, what I just said does have practical value. You can check the first column. You can solve it using the first row, but you should use the second row to check. If something is wrong, that means you made some error above. All right. So plug in, we got minus. So this is going to be 4. And this should be minus 2, right? Minus 2i. And then that should be 2 minus 2i. Right? Okay. All right. So now what is v then? Well, I think, right, in this case, it's up to you, but one of the common technique would be to try to do the conjugate on the first one, unless, you know, there's a better thing to do. So if you do that, right, minus 2 minus 2i times minus 2 plus 2i, right, will be 4, right? A squared minus b squared, which is 4 minus 2, which is 2. 4, wait, hold on. A squared plus b squared plus 4, which is 8. Okay. So that means this one should be -4. Or, right, that could be just simplified down to -1 plus I and -2. Now let's check, okay? Let's check using the second row. On the second row, we got -4 times 1 plus -1 plus I, right? Plus 2 minus 2I times -2. If our solution is correct, that should be equal to 0. Okay, so let's see here. We got 4 minus 4I, and then this is going to be -4, right? Plus 4I. Correct. Okay, so our solution here is indeed that. I mean, this is not equal, right? Maybe let me clarify. So another choice will be this, because eigenvector, right, does not change by multiplying by a constant. So that works. All right. So any question here on solving for the eigenvector and eigenvalue? All right. So now you don't need to find the second one for the complex eigenvalue, eigenvector, okay? Because we will construct our solutions, right? Construct the two solutions from the complex solution above. So in other words, right, you start out with yt, right, which is v, right, -1 plus I minus 2 e to the lambda t, which is 4 plus 2I t. Okay. Now, then you use Euler's formula on the exponential term, right? E to 4t out, cosine 2t plus I sine 2t. Okay. You combine these two. So you got minus cosine 2t, right? And then plus, right? Minus sine 2t plus I cosine 2t minus I sine 2t. The second one gives you minus 2 cosine 2t and then minus 2I sine 2t. Now you separate the real part and the complex part. Minus cosine 2t minus sine 2t minus 2 cosine 2t. I cosine 2t minus sine 2t minus 2 sine 2t. So this will be your y1, and this will be your y2. And some cosmetic change is fine, right? In other words, I can make everything here into a plus because there's a constant multiple. So in other words, right, my solution will be e to 4t, right? C1 cosine 2t plus sine 2t, 2 cosine 2t, plus C2, I'm out of space, right? Plus C2 cosine 2t minus sine 2t minus 2 sine 2t. That's my solution. Any question here? Yeah, e to the a plus bi is e to the a cosine b plus sine b, I sine b. So I'll get to you, Ron. But Carl, I mean, actually, it's very simple. I think it all only comes from this e to ib. Just remember, basically, is this. It actually is strongly motivated, and actually is the same thing as the unit circle for cosine and sine. If you remember your trick, cosine sine. Yeah, I'll get to, so I'll go to Carl and then Ron and then Sarah. So cosine sine, all right? So there's an angle, all right? And that angle is exactly B. So then if you remember that, an e to ib is just that guy right there. Then exactly, this is cosine and this is sine. Just remember that the sine has an I attached to it, that's all. Because, in a complex coordinate, I is the y coordinate. And so that's exactly, so sorry. So what I mean is this. So this whole thing, right, really boils down to, on the clock, right, on the unit circle, is cosine plus I sine. So it's really x coordinate, y coordinate. All right. All right, Ron. So Ron, your question is very interesting. Let's see, right? How do we address this? So first of all, right, there are two layers to your question. So first of all, last time we did say this. Suppose y of t, right, has two components. All right. So if right, y of t is a solution, then y1, y2 are also solutions from last time. Okay. Now, Ron's question, right, or a more general question is why y1, y2 must be independent. I mean, as in coming from, right, coming from like the structure of the eigenvector, right, like this. Okay. So first of all, right, I do suspect there is a reason why. I think in general, they should be independent. Okay. Now, I can think about it and I can tell you, I can play with it for 2 seconds, right? Because I don't want to distract from the lecture and it add too many, confusion maybe. But first of all, Ron, right, I don't have an immediate question for you right now. I do suspect is that the structure will drive it that way. It's the same thing as you're saying, the independence roughly comes from even the independence here between the real part and the imaginary part. Okay. But here's this, right? I can give you a partial answer like this. Well, this is always true. This is always true. So you can play it by pure chance like this. If you observe that these two are independent, then the theory applies and you can just go ahead and construct a solution out of this because they're independent and they are solutions from this. So this conclusion is always correct, right? Now, your question, of course, is much more interesting, right? Why does it reliably produce independent solutions, right? That needs some kind of address. But my partial answer, my wiggling way out is, if you eyeball it and you see that they're independent, then you can just construct solution out of it. Okay, but to answer your question more carefully, I have to think about it. All right. Sarah, how I got V1? Yeah. Okay. Ron, is that okay? Yeah. So let me comment one more. I think it has something to do with, right? Suppose that you got AV, okay, is equal to lambda V. And suppose V, right, is V1 plus IV2, then V1, V2 must be independent. All right. Actually, I think I can show you why. Okay, sorry guys. It's just the math person in me. I got a good question and must answer it. 1 second. All right. Let me play with it. I know the answer here on. The answer is this: that if suppose not, then V1 must be a constant times V2, right? So if you plug that in, then V will have the structure like this: V1 plus I C V1 would be something like V1 times 1 plus IC. But then plug that back into the eigenvalue, eigenvector structure. You got something like A, right? Let's say V1 plus IV2, right? Or, yeah, would be lambda, right? V1 times 1 plus IC. Okay, so and then, okay, I think I'm going a little bit too far afield. You also plug in here. My intuition is that somehow if you see this, then you see something's wrong with the lambda. Because remember, in this case, lambda must come in conjugate pair. So if you also plug this into here, you will get some contradiction, I think. All right. That's my hunch. All right. Sorry for the rest of the class. I'm just get hooked into this question, but don't worry about this. All right, it's a side question. All right. But that I think, Ron, is the direction to go. Okay, Sarah. How to find V1? Okay, where was it? V1. All right, here. So how you do it, right? How you do it, Sarah, is this: that of course, right, is always solving for V1 equal to 0, right? That's always the case. Now, of course, if these are real coefficients, then we just eyeball, adjust coefficients. I think eyeballing complex coordinates is not that easy for us. At least for me, I don't play with complex numbers too much. So the trick, right, is to convert that to a real. Okay. First of all, you should be confident that if you solve for eigenvalue correctly, all right, which I did not first time, but if you did solve it correctly, then these two equations say the same thing. Okay, these two equations say the same thing. So you can use one of them to solve and the other one to check. All right. So let's say you use this to solve. If you use this to solve, right, the most common way to convert a real eigenvalue, sorry, a complex thing to a real number is to multiply with its conjugate, following this rule that a plus bi times a minus bi is a squared plus b squared. Okay, so I use that here, right? This is minus 2i, right? Then maybe not the most efficient guess, but a straightforward guess is minus 2 plus 2i. And you see that's where my calculation is down here, right? You'll get 4 plus 4, which is 8. But if it's an 8, then I must compensate with a minus 8 here, hence the minus 4. Okay. Then immediately I see that, well, there's a bunch of 2's here, so let's reduce that down to this. So that's just a reduction, right, by dividing by a constant. So now, basically, I got this from looking at the first row, okay, by using the conjugate of this guy. And then, right, I would, to make sure that this is correct, I use this and I plug into a second equation and check. And if, right, things cancel out to be 0, then I'm very good. Then that must be right. And that is the approach. Is this okay here, Sarah? Yeah. Any other question? All right, so let's give you a trivial 3x3 example, right, and see what happens. Okay, so 3x3 happens exactly like 2x2, but let's give you an example for you to see. Okay, so let's say y prime is, let's say 2 0 0 0 0. Let's say 2 I don't know, 3 3 1 minus 1 y. Okay. I'm making up a matrix that makes it very easy for me to calculate, the structure I want. So for those of you who kind of are interested in linear algebra, right, this matrix has something called a diagonal block structure. So basically, I'm just reduce it down to a 1 by 1 and a 2 by 2. So, but just to demonstrate an example, all the examples would come down to that. But what I want to say is this, that in a 3 by 3, right, remember the statement I said before holds for in general. In other words, complex eigenvalues, right, always comes in conjugate pair. Okay, what that means is if you know is an eigenvalue, then A minus BI must also be an eigenvalue. No question. Okay. What that means is this, right? Let me ask you this, right? And I hope this is clear. What that means is, can a 3 by 3 matrix, right, 3 by 3 system has 3 complex eigenvalues? Can a 3 by 3 system has 3 complex eigenvalues? No, right? Exactly. So exactly. No, the matrix is real, Daniel. Yeah, for sure. Correct. So, right. So in a 3 by 3, you can guarantee that you would have 1 real and 2 complex. Exactly. That's what I'm saying. So in a 3 by 3, you will always have 1 real and 2 complex. 2 complex conjugates, right? So exactly, in a way, it's just the 2 by 2 case, right? Soup up with 1 more real solution, right? 1 real eigenvalue. That's all. There's nothing complex about 3 by 3 in this case. Okay. So, but for purpose of demonstration, right? Let's look at this system and let's show you how to go about, right? So first of all, what is the determinant of a minus lambda? Determinant of a minus lambda I. So it will be, right, 2 minus lambda, right, times, and you see where this is where my blocks come in, right? 3 minus lambda squared plus 1, right, is equal to 0. So lambda equals to 2 and lambda equals to is 3, right? Plus minus I, okay? So each of, and by the way, right, because of that, in a 3 by 3, you always have distinct, right, eigenvector values, eigenvectors, except of course these guys will be complex. But so then you solve for each, right? Lambda equals to 2. Let's see. Lambda equals to 2. What do we have, right? 0 0 0 0 3 1 0 minus 1 3, right? So what is the eigenvector here? Oh, what am I doing, right? Apologize. It should be a 1, 1, right? Anyway, it doesn't change that. What's the eigenvector here? Should be 1, 0, 0. Yep, exactly, right? This right here dictate that the two other coordinates must be 0. Okay. Now, similar to the other ones, right? You do not have to solve for both. Just solve for one. Let's say 3 plus I. Okay, let's say 3 plus I. Then what do we get? We got minus 1 minus I, right? 0, 0, 0, minus I, 1, 0, minus 1, and minus I. Okay. All right. So what's the eigenvector here? I think 0i minus 1 seems like a reasonable choice, right? Is that okay? So I don't need the third one, all right? I don't need the third one. Why? Because this and this together will give me the pair. So what does that mean, right? What that means is I already know my y1. Y1 will be 1, 0, 0, e to a 2t coming from here. Okay. Now to produce my y2, y3, right? I will do the separation that, or conversion, whatever that means, right? Realification that we had before, which is what, right? 0 I minus 1, right? E to the 3 plus it. And I will separate these, right? It will be 0 I minus 1, right? E to 3t out, cosine t plus I sine t. Mix them up. Minus I sine t plus, sorry, minus sine t plus I cosine t, minus cosine t plus, rather minus I sine t. So we got e to 3t times 0 minus sine t minus cosine t plus I 0 cosine t minus sine t. Is that okay? So my total solution will be C1 1, 0, 0, e to 2t, e to 3t, C2 0 sine cosine, C3 0 cosine minus sine. Any question here? Where did I do something wrong? You mean, oh, right here? Oh, no, Ron, it's not assumed. It's, it's exactly from this result that I stated last time. So it's not assumed, all right? You might think it's assumed, which is okay, but no, the logic goes a bit deeper than that. The logic is that if you have a pair solution like this, then the real component is a solution, and the complex components also, the imaginary components also are also real value solutions. So real part of solution and imaginary part of solution are also solutions. Of course, right? Like I guess Daniel was referencing that you got to get real value, but that's always what we're in to begin with. But yeah, so same logic, right? Same logic applies here. Any other question? Do you want one more example, or do you think this is sufficient? Yeah, thank you, Jetan. But that doesn't matter, right? Because my C2 can take on any value. So I'm free to drop this if I want, right? Same thing as here, actually, right? I use the same trick here. Where was it? Right? I got all the bunch of minuses here. I drop them here, understanding that C1, C2 are free to choose. So that's actually fine. Yep. All good. Oh, you want one more example? So I'll take the silence is all good, I hope. Okay. So then that's the analytical part. Okay. Now let's talk about the sketching solution, right? And classifying equilibrium. Yeah, I mean, let's just write 2 by 2 here, right? We can do 3 by 3, but I guess the concept gets it'll get a little more hairy on how to kind of file them. So first of all, right, let's remark that the system we're looking at, right, y prime equals to ay, okay, has two complex eigenvalues. So for that matter, right, because of that, the ay, right, equal to 0 solution also has only, right, 0 as the solution, because you don't have 0 eigenvalue here. Okay, the matrix is still invertible. So in other words, what do I want to say here? That 0, right, 0, 0 as a point, the origin is the only, right, equilibrium solution. Okay. So we want to classify this origin and also want to sketch a few solutions, right? So the eigenvalues, right, will be of this form. Okay. So we'll have cases, but the case will be dependent on the sign of A. All right. So we have 3 cases. Case 1, A is positive. Then the origin will be classified as a spiral source. Okay. I think it's clear. So first of all, let me write this. Basically, because of this, right, the solution will be something like this. C1, so e to at, right? And then C1, some cosine sine in terms of b, and then C2, some cosine sine in terms of b, right? Like that. So you see, it's the sine of A that drives the direction of the solution, right? The growth or decay of the solution as time goes on. This right here, right? The B, the contribution of B is it only contributes to the so-called, frequency, right? The period of the solution, and it will contribute to the the circular nature, right? The spiral nature of the solution, or the periodic nature of the solution. Okay, because you have a periodic component in your solution, so you will have, right? I mean, so the B part plays a role in the frequency, the A plays a role in the magnitude. All right. So because if A is positive, it's clear that this part goes to infinity, and that's why it's a spiral source. Solutions sketch is as easy as it gets. Not much you can do except to draw something like this. I don't know. Right, like that. So actually, right, I'm fudging over some details here. Detail, right, to be determined is the the direction of the revolution. Clockwise, counterclockwise. All right, because I mean, right, you could have a spiral source the other way, right? I don't know, like that maybe, right? This is also a spiral source. How do I settle which picture is roughly correct? How will I do that? Oh, the answer is actually quite simple by checking the direction field. Okay. I mean, you got y prime equals to ay, right? In general, sketching the direction field is a painful job for the computer. But if you just want to know if it points this way, it points that way, well, right, pick a point, calculate this, sketch that vector, you should know which direction it should follow, right? If you just want to settle this picture, then do one calculation at some sample value of y, then you get that. Is that okay? So let's see, right? The ones that we did before, was it both positive or was it positive or negative? So it's positive, right? It's positive. So what was the matrix? This matrix, right? 2, 2, minus 4, minus 6. Minus 4 and 6. Okay. I don't know. I mean, let's just check at like y equals to, I don't know, 1, 0. then, right, the direction is 2 minus 4, right? So I wonder if that gives you enough. But so 1, 0 is here, right? And 2 minus 4 would be go to the right 2, go down 4, so it's like this. So which direction should the spiral go? I believe this direction, right? Okay. All right, so case 2 is when A equal to 0. All right. When A equal to 0, so see, then there's no growth, right? It's pure circling. It's pure circling. Then the origin is the center, right? But be careful, right, to not take this word center as in like the center of a circle, right? The orbit, right? The orbit can still be an ellipse, right? The orbit can be and should be, right? Can and most likely, right? Still be an ellipse, right? So when we say circle, that's just a terminology to use, but it's not really, you know, like, sorry, when we say center, right? It can be center of an ellipse if you want. So again, actually here, right? I think the picture I draw is quite simplified. Maybe there's another detail to determine, like there's the direction of the spiral, but there's also like kind of like another one would be the tilt, right, of the spiral, maybe, right? There are more than that, but I think for our interest, I only care for, you know, the spiral, right? Spiral source, spiral sink, and its direction, like of circulation, right? Because for example, right, if you have an ellipse might look like this, right? Or it might look like this, for example. Okay. And the direction of circle, right, could be this, could be that, for example, right? So, right, this is what I mean by the tilt, right, of the ellipse. And that again has to do with the eigenvector, right? The eigenvector, the direction of the eigenvector. So details to determine, right? Direction of rotation, right? Axis of the ellipse. Again, right? Direction of rotation, you should be able to get from the vector field, right? But the axis of rotation, right? Well, let's not. I won't hold you to that. But if you want to think about it, that'll be an interesting question on how to easily get that, for example. And by the way, right, there could that's just one ellipse, right? Basically, the solution curves will be a bunch of ellipses, right? Depending on how you start. So it's not just one ellipse, right? One ellipse for one initial condition, right? And you can have many ellipses depending on where you start. Last case is for a negative, all right? And it will be a spiral sink, right? Again, because as t goes to infinity, this goes to 0, right? And this provides the circling component that goes down to 0. So again, right, some rough picture, but can be improved on a lot. I don't know, right? draw something like this, but it will circle in, right? But which direction, for example? Okay, so which direction? Also the tilt, right? And the kind of the scale that I'm not capturing in the picture, but the rough. Okay, so 0, 0 spiral sync, and the rough sketch is like that. Any question? So Albor, your question is would the spiral crosses, right? Is that your question is? The answer, you mean given the initial condition, not initial rate of change, because we only given y0, right? We don't give y prime 0. But of course, from y0, we can figure out y prime of 0 too. But the answer is no, right? Because of uniqueness, right? The solution curves won't cross. All right. Now, of course, with my amateur drawing, right, it's hard to see why another spiral won't cross it. So let's take a look at the book, okay, to see how the spiral proper is drawn. Well, so first of all, right, keep things in mind. A second order equation can be reduced to a first order system. So something like this. Then what picture are we representing, right? Here, the picture representing, if it's second order equation, then this is representing the solution and its derivative, right? But because the solution is unique, does that mean its derivative also is unique? Okay, so the solution to a system is unique. Let me put it that way, okay? The solution to a system is unique. That is true. So therefore, like the solution curves won't cross. If you cast the second order equation as a system of first order, then you use the theory, right, of uniqueness of first order system. So in that regards, no, these curves won't cross. If it's linear, if it's a simple y prime equals to ay, solution curve won't cross at all. If the initial conditions are different, right? Yeah. Mm-hmm. Yeah. So let's take a look at the picture in the book. So, for example, right, this system, they say is a spiral source, right? It's a spiral source. Well, so why? Because here's the eigenvalue, right? The real part is positive, so it's a spiral source, right? And you see, right, the direction of rotation can be inferred by the direction field. Okay. Now, I don't know, like in connection with Albor's question, right? I believe another spiral would look like that. Another spiral would look like that. Okay. And you see how these spirals cannot cross each other. Is that okay? Not like my, you know, crude spiral that does not inspire much artistic value. But also notice there's a tilt here, right? Not like a complete circle, that kind of thing. Okay. This, I think, is a center, right? This is a center. Why? because, wait, did they even produce that? I think they might draw it down there. Hold on, this is a different one. Yeah, it's really a center. For here, A will be 0. I think you can just see it from, the picture, right? Like that. But here, right, this system is what I want to refer to, right? So here you see lambda is plus minus I. So the real part, right, A is equal to 0. But you see, right, there's a tilt, right? There's a tilt from the eigenvector. Did I produce eigenvector here? I don't think they did. But right, see the ellipse is like this, right? The ellipses are like this. And of course, these are like the bigger ellipse out there. Okay. What about this, right? This, let's see. What are the eigenvalues? 1/2. So it's also a spiral source, right? It's a spiral source. It goes out. Yeah, you can tell, right? You can tell it goes out like that. Yeah, right. I mean, is for example, for this picture, okay, first of all, there's a very beautiful tilt, right, that I did not draw. But second, again, it may be hard to see, but another spiral, right, would loop around, but manage to avoid the other spiral completely, I think. Must be. These two, if you draw no spirals, right, they don't cross. Except, of course, they seem to cross at 0. But 0 is not a material point, right? 0 is a point at infinity, so that doesn't matter. Okay. Any question here? So I think there's like this fun question to look at. Can I make it smaller? Right here, this question. Okay, number 15. So 15 is not something that we care so much about because we always draw, phase curve. So we draw x versus y. But the book does like to talk about, how the x solution, right, can be graphed separately, right? This is like the marginal graph. And they asked, right, basically among these guys, which one seems like a legitimate graph, right, of a system with complex eigenvalues? After you identify those legitimate system, what's the natural period? I think that's B, right? That's the B. How long does it, circle back? And right, 0, 0, is this sinc source or center? And then I guess explain why the ones you don't choose fail, for example. So give it a shot. That's going to be the last thing that I will do today. But I think it's kind of fun to look at that. So let's do A first, right? Which one do you think is legitimately coming from a system with complex eigenvalues? Yeah, I agree. Anything else? I have reason not to choose one. I have reason not to choose one. 4, yeah, 4, I agree. 4, I agree. 1, I don't have faith on. I'll explain. Okay. Yeah, that or some other stuff. Anyone rooting for, the poor loners out there, these guys. Okay, so let's quickly explain why we strike these guys out. I guess this and this seems to have the similar explanation, right? That basically somehow the oscillation stops here, seems to stop here, right? But then how about this? So actually, right, there is a thing about the complex system that we're looking at, all right? It's not general in real life, but for this one, is that notice it's always A plus BI. And so the cosine sine will be cosine BT, sine BT, that kind of thing. In other words, the complex system we're looking at, okay, will always have same period going forward in the future. So the periodicity never changes as time moves on. Okay. So notice, right, one, it gets faster and faster, right? The frequency gets higher and higher as time moves on. So odd beginning or not, right? The fact that it starts to get bunched together means that the period starts to getting smaller. That doesn't come from this system that we're looking at. Okay. The nature of the constant coefficients of A. Yeah, or it has a driving force. It has a driving force. It could be linear, but there may be something outside that's driving it. There's a FT, remember we say that? Yeah, I don't know, right? Yeah, non-constant coefficient could be it. But so Albor, so be careful. You're saying non-linear, that's a bit too much. I think non-constant coefficient may already cause it. Like suppose a coefficient of A, right, change with time. That will mess around with the with the period. Right. So this is out. I think for similar reason, right? You can see these don't support same periodicity. So all this out for some reason. Okay. And then for this, right, it's clear that this is a spiral sink. This is a spiral source, right? Because the magnitude, right, goes down. This magnitude goes up, or intensity, right? That's what we call it. All right. Any question about this? All right, sounds good. Then if there's no question, I'll see you next week. Okay. Thank you. You too. Thank you. You too.